Well, here we are, Chapter 11, and I'm going to talk about intermolecular forces this time. No calculations here, but there is a lot of stuff to keep straight in your head. So, students sometimes have trouble with this chapter. So I want to walk through the intermolecular forces and do an example problem, kind of the thinking process that I think you should be able to, kind of execute fairly quickly to get, to do really well on this type of question on future exams and stuff like that. So intermolecular forces, and so let me write it out here for just a moment. Intermolecular forces, okay? Hold large numbers of molecules together. Okay. Now, notice I said that, large number of separate molecules together. These are the forces that give us the condensed phases of matter, that clump things together in liquids or often into solids. Okay? It's not as simplistic as that, but that's a good first pass at it, that weak intermolecular forces tend to be associated with things that are gases, strong intermolecular forces, things that are associated with things that tend to be liquids and or solids. So the three intermolecular forces that you really need to keep in mind, okay, is, and let me just write this one out here, dispersion. And sometimes dispersion forces, London dispersion forces, whatever. Dispersion, that is the most basic one. Basically, all matter has this intermolecular force involved. It's sometimes associated with polarizability. It is the only intermolecular force in non-polar substances. It tends to be weak, but size plays a big role in this one, okay? You see it a lot in non-polar molecules. In fact, it is the only intermolecular force in non-polar molecules, but it has one major ally, and that is size. The larger the atoms, the larger the molecules, particularly if they have more and more contact with each other. The dispersion forces, inherently weak, can actually get quite strong if you're dealing with considerably, very large molecules. So this one is an important one. The other one, dipole-dipole interactions. Okay, polar molecules. Molecules, cool stuff. Polar molecules. Now, this one is usually thought of as being, often stronger than dispersion. Although there are exceptions of that. Generally, we put dipole-dipole in the middle position here as the second strongest intermolecular force, although, size can really make dispersion compete well with it. So that's a kind of a dicey one, but dipole-dipole. Molecules that are polar, okay? And we'll see several examples. You've seen several examples. We'll see several more. And then, of course, the big one, hydrogen bonding. Okay. The strongest of the intermolecular forces, the rarest of the intermolecular forces, confined to only three kinds of molecules, those that have very highly electronegative atoms that are very small, attached to an even smaller hydrogen atom. HF, NH, OH. Molecules that contain those bonds are going to be hydrogen bonded. You have the hydrogen bonding intermolecular force, which is the strongest intermolecular force. Okay? And so those are really important to be able to spot, and they're fairly easy to spot, and we'll see that in just a moment. So remember, keep this in mind. The three kinds of intermolecular forces and a rough guide to how strong they are. Dispersion forces, generally the weakest, but it has a big ally in size. Dipole-dipole, usually thought of in the middle. Polar molecules, And then finally, hydrogen bonding, rare. It only occurs in these kinds of molecules here, but it is the strongest of the intermolecular forces. And so now what I want to do is turn our attention to problem, and that was the one I selected, 11.28 out of our textbook here. And it's one of those classic problems that has, here's some molecules, tell us which one has the weakest, which one has the strongest intermolecular forces. So you do have to have in the back of your mind this basic information. So what I'm going to do is we're going to put the text of problem 28 up, take a quick look at it. While we're doing that, I'm going to apply the magic eraser and clear some of this space, and we'll start tackling the questions in this problem. There. Now, this particular question, problem 1128, gives you several molecules to look at and asks you for each pair that they want you to take a glance at, which one has the highest boiling point. Okay. Now, like in other chapters and other contexts, there's lots of ways to ask this type of question, which one has the highest boiling point. In reality, what they're asking is, which one of the following pairs of compounds has the highest or the strongest intermolecular forces? They can ask that question by saying, which one has the strongest intermolecular forces? They could say, which one has the highest boiling point, which is a common way of getting a measure or a feel for strong intermolecular forces. They could say, which one has the highest melting point, which one would form the most viscous liquid. There's all kinds of ways they can ask the question, but they all have roots in which one has the weakest, which one has the strongest intermolecular forces. And that's the strategy I'm going to use when I'm comparing these. So the first set, part A of this problem, they want us to look at C3H8 propane versus C4H10 butane. Now, what you need to do is to be able to look at the molecule, the formula, and probably a good idea to look at the structure, remember its geometry, decide if the molecule is or isn't polar. Doing that with these three here, putting hydrogens at each of these positions, a bit tedious, but we'll do it anyway. Carbon, 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 boink, 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 boink. Put a hydrogen in each position. Okay, there are the Lewis structures, each of the carbons tetrahedral. Lovely little Lewis structures here. And we look at these and should be able to, using our chapter 8 knowledge, be able to look at these things and say nonpolar and nonpolar. Now, going back to our listing of intermolecular forces for a moment, they are both nonpolar. Therefore, the only intermolecular force we need to think about is dispersion. And dispersion forces have one ally, and that is size. Okay? And so when it's a question of nonpolar molecule versus nonpolar molecule, often what you want to think about, okay, which one has the strongest intermolecular forces? Which one is larger? And that one clearly is the butane, and that's the one we're going to pick. Okay? This one will have the strongest intermolecular forces, the highest boiling point. Given a choice between these two, our answer for part A is butane. There we go. On to the next one. Part B. They want us to look at diethyl ether versus, which one was it? Propanol. All right. Now, for diethyl ether, okay, they give us this information, CH3, CH2, CH2, CH3. Writing that out, you can almost kind of see how this is going to go. You got an oxygen in the center with two identical things on each side. Yep, that thing is actually bent. And I'll just go CH2, CH3, boink, 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 CH2, CH3. This one is bent. Okay, bent structure, it is polar. Okay, therefore, the intermolecular force to think about here is both dispersion, found in all matter, and, okay, dipole-dipole. And then they give us propanol, okay? And they go CH3, CH2, OH. Now, be in the habit of looking out for these, because it does make life quite a bit easier when you see it. There it is, OH. Ding! When you see that, you should think to yourself, Hallelujah, Hallelujah. Yeah, you should think to yourself, there it is. That's a hydrogen bonder, okay? Hydrogen bonding. Exclamation point, exclamation point, exclamation point. Right off the bat, I don't have to draw anything else out. This one has the strongest intermolecular forces. That one has the highest boiling point of these two molecules. Hydrogen bonding, that is always a good one to look for. Be able to spot it, okay? FHOHNH, okay? It popped up here very readily. There it is. That's the one. Part C. This one, sulfur dioxide versus sulfur trioxide. Now this one right off the bat is a little bit ambiguous, and so what you need to do first is draw the Lewis structures of these things. Go back to earlier skills back there in chapter 8 and chapter 9, and I'm going to go ahead and do that, and I'll do it fairly quickly here. This one will turn out to be bent. It has the two resonance structures, but I'll just draw that one for the moment. Bent. Sulfur trioxide, if you draw its Lewis structure, will come out this way. And it is trigonal planar. Now, so there are the two Lewis structures. We look at these and we make the decision, is it polar or is it not? And this one is polar. This one is nonpolar. Okay? And so of the intermolecular forces here, this one, dispersion, and dipole-dipole. This one, dispersion only. Now, given all that, your choice is which one of these would have the highest boiling point. In other words, which one of these has the strongest intermolecular forces. Now, this one, to be honest with you, I found this one from the textbook to be somewhat ambiguous. And in fact, I probably myself would not have asked this one, at least not without further information, because it is ambiguous, okay? There is no way, given just what we've been talking about, to make the decision which one of these would have the strongest intermolecular forces. Sulfur dioxide is polar, therefore it has the dipole-dipole interaction, which is usually thought of as being stronger than dispersion forces, so that favors sulfur dioxide. But sulfur trioxide is larger, and being a trigonal planar molecule, two of these things could get in fairly close contact with each other with a lot of area to contact each other and interact. And so you could make an argument that this one, as being larger and flat, its dispersion forces will overwhelm the polar nature of the sulfur dioxide. And so, to be honest with you, in my opinion, this one is a little too ambiguous to be a good question to be asked here at the end of in an end of chapter question, or even to be used on an exam or something. You want your examples to be a little bit more clear-cut than this one. It turns out, if you look up the information, this is the one that actually has the highest boiling point. It turns out the size and the planar nature of the sulfur trioxide outweighs the polar nature of the sulfur dioxide. But in my own opinion, it is not reasonable to expect undergraduates in a freshman class in particular, when we're just getting used to doing this sort of thing, to be able to make that prediction. So for this one, I really think it is kind of an unfair comparison to try to make for these reasons. So there it is. That's the analysis of it. And I understand this one's probably the toughest one of the bunch, and I won't be using something like this myself. So let's get on to the last one. Part D. Okay. Now they want us to compare these two molecules, phosgene versus formaldehyde, H2CO. If you draw out the Lewis structures of these two, we're going to come out with these structures. Okay, and for phosgene, or for formaldehyde, we're going to come out with that structure. Very similar type structures. They are both trigonoplanar. Three regions of electron density around the central atom, trigonoplanar structures, therefore they are both polar. Top side, bottom side of these both molecules are different, so one side has a different feel, a different electric, electric distribution than the other, and both polar, so they both experience dispersion and dipole-dipole. Now, in this one, you might think off the top of your head, oh, there's another ambiguous one, but it's really not. This one you can make a pretty good prediction on. Now, the earlier examples we had, you were comparing two, the same intermolecular force in the first part A, dispersion forces, but one was larger than the other. That was easy. In the second one, you were comparing a polar versus a hydrogen bonded molecule. That one was easy. In the third one, that one was a little bit ambiguous. In the fourth one here, again, it seems like it's a tie, but you would look at this and say, dipole-dipole for both of them, that ought to be pretty strong. Dispersion forces in both of them, and this one is the bigger one. And so I'm going to give the phosgene the edge in this one for having the highest boiling point, the strongest intermolecular forces, simply because they both are polar, both have the same geometry, but this is the one that is larger. It simply contains larger atoms, more polarizable. Therefore, I'm going to say that one, okay, on the basis of the fact that its dispersion forces will be stronger than they will be in formaldehyde. And so there it is. It's not that difficult to do. Once you have pretty firmly set in your mind the three intermolecular forces, dispersion, dipole-dipole, hydrogen bonding, and a feel for their relative strengths and what factors go into making them weaker or stronger. Okay? Keep those ideas in mind, practice several of these, and you get pretty good at being able to spot those, particularly the hydrogen bonders. Those are nice to pick out because they clearly point in one direction to strong intermolecular forces. When you're trying to come up with a list, decide which one has a higher boiling point, or any of the other variations in questions that they can come up with in this type of material. So think carefully about intermolecular forces, go practice a few of these, and see you later.